So first thing, give the features of the scatter plot. Let's see if we were following along with what we were talking about yesterday. Three things you should say. Well, aside from like talking about if there are any like outliers or unusual values, which I don't think there are. What are the three other things that we talked about yesterday that we should talk about when we mention a scatter plot? This will make things more difficult. It's linear. That's one thing. Two other things I want to talk about. That is form. That's kind of like shape. Positive, right? As temperature goes up, the visitors go up. So that is direction. And then the third thing is strength.
That's hard for me.
Strength, direction, and form. And so fairly strong, I would say. So strength, direction, and form. And I usually have people write it in that order. A fairly strong positive linear association between, what are my two variables? Visitors. So which one is the response variable? It's the visitors. The response variable is y. The explanatory variable is the temperature. So in other words, explanatory variable is temperature because we're using temperature to explain the beach visitors. So we are saying that as the temperature will go up, the amount of beach visitors will also go up. That makes sense? Okay. Now this brings up a term that I did not talk about yesterday, but that is important to make sure that we avoid, which is extrapolation. This is something that we want to avoid. Extrapolation means that I use data that is outside of the data set to try and draw conclusions. And so what we're looking at is how good of a predictor the temperature will be for the amount of visitors to the beach. And we're saying as temperature tends to increase, so does the amount of beach visitors. But we can only make conclusions if we're staying inside the range of temperatures that we actually got data about. Once we're outside of the range of what we collected data about, then we should be very cautious about making any kind of conclusion. For example, in this situation, about how many, let's say about 90 degrees. If it were 90 degrees, about how many visitors to the beach would you expect? Here's 90. So with my trend, maybe my line of best fit would be about here. So if I'm at 90, how many beach visitors should I expect? About 450-ish, maybe a bit closer to 500, depending on how we draw the line. That's okay. We can make predictions. That 90 is inside of the set of data that we're, the range of data that we're looking at. What if the temperature is 150 degrees? How many beach visitors would we expect?
Probably none.
Probably none. It would be a very bad idea to go to the beach. At that point, you would not want to go to the beach. And so we would not be predicting that the trend would be all the way up here. That would be a bad prediction. And because it's outside of the data set, we should not make a prediction like that because the trend may change as we continue in the data set.
So, because technically, if you set the precedent where you were like, well, at 150 visitors or at 150 degrees, it would be like higher. You
Right.
could just keep going up exponentially, and it'd be like. Well,
Not exponentially, but in a linear way.
Temperature was like 3,000.
We'll talk about when things go up exponentially later on. But yes, it would be a bad idea to say, all right, at 300 degrees, well, there's going to be like a few thousand people at this beach.
Yeah.
Then we would all die.
We wouldn't all die at 150 degrees.
I wonder what the time to like kill is as a temperature. How long would it take you to die? 300.
150, you could probably maybe survive a little bit.
For like an hour.
No.
No, less than that. But when you get to 300.
Because I have a friend who was in California last week that hit like 110 for like 2 hours or something.
Mm-hmm.
And he said that they recommended, the like weather people recommended that you only stay out for like 20 minutes or something.
Yep. Yeah. Once it gets to that kind of humidity.
In Boston, we sometimes visit in like the summer,
Mm-hmm.
and there's a city, Lahore. It's southern, and it get like in the summer can get up to like 120.
Yeah.
With a heat index of 130, and sometimes like the electricity will go out, and it's so bad. It's so bad.
Oh, heat index of 130 with no power and no air. Numerical way to make us quantify the amount of. So we talked about the strength and how strong the trend is. That was one of our measurements that we were talking about. And a way to numerically measure that is with R. And R is a correlation coefficient. Correlation coefficient. And so we can use it to stand for, that can kind of give us a strength, direction, and form quantified into one number. And so you'll notice in this example we did yesterday, there was a little R equals negative 0.87. There's a big long formula for it that you won't have to calculate. But what it is measuring is essentially how close to my line would my predictions be. So how close are my predictions in relation to where the values that we actually got the data on are. So some things about R. Okay, R does not depend on a unit of measure and doesn't have units. So the relationship between height and weight is equally strong if we use inches and pounds or centimeters and kilograms. And a key thing to say here is that it has no units, and that's said again down here. R has values between -1 and +1. And you can think of this as a scale of extremes. So the closer R is to one extreme or the other, the stronger the association is. The closer to 0, the less the association. 0 would mean that there's no association at all between the variables. And an R value of 1 means that every single point is on the line. That X can be used to perfectly predict Y. That's usually not going to happen. But the closer we are to 1 or -1 on either extreme, the stronger the association. Closer on the +1 end is going to mean that we have a positive association that's very strong. Closer on the -1 end is going to mean that we have a negative association that's very strong. So I had -0.87. Well, that gives me strength. The 0.87 is a fairly strong association, and then the negative tells me that we have a negative linear association. The actual scatter plot tells me that the pattern is linear. Some more things. Like I said, if we are at +1 or -1, then that means we have a perfectly straight line. Every point in the scatter plot is on the line. And R shows the strength of a linear relationship. It measures how closely the data fall to a straight line. R value near 0 doesn't imply that there is no relationship, only no linear relationship. So, for example, let's say that I had a set of points that looked like this. Right? Not a linear relationship. And the line that I might draw, the line of best fit that it might come up with is something like this. And the R value is going to be not as good. But that doesn't mean that there's not a good relationship between them, between the two variables, and we can't use it as a good predictor. It just means that a line is not the predictor. The curve we want to draw would be more like this. And then if I use some type of function like this, then I would get a very good correlation coefficient in that case. But it could also mean that there's not a strong linear, that there's not a strong relationship in any case. So this is out of the book here. So here's an example of a correlation that's close to 0. Here's a correlation of -0.3. So you can start to see that there's, starts to be a trend of as one goes up, the other goes down, but it's not very clear. Here's a correlation of +0.5. So now you can definitely see that as one is going up, the other is going up. But the points are really spread out. I would probably describe this as a weak positive linear association. And then as we get closer to +1 or -1, then my relationship gets stronger here. Here's -0.7. Now we can start to see the pattern and maybe start to be able to show where the line of best fit is going to be. Here's 0.9, even stronger. Here's -0.99. Now you'd be very hard pressed to miss the line of best fit. So as I get closer to those positive and -1, the association becomes stronger and stronger. Again, R is not something that you will have to calculate. It is something that will be told to you and that you might have to interpret. That's the idea. One more thing about R. R is called. Why is my smartboard not working all of a sudden? There we go. R is called the correlation coefficient. And so just remember that is, if you see correlation coefficient, you should think R. Because sometimes it'll ask about the value of the correlation coefficient or to interpret the correlation coefficient. And you, like the AP test will ask you and just say the correlation coefficient, and you're meant to know that that means R. So just don't forget that R is called the correlation coefficient. let me talk about that word correlation very quickly. Because it's important that you understand what something being positively correlated means. If I have a positive correlation, that means that all that means is that as one variable goes up, I can make a good prediction about what the other variable is. In other words, I can use one variable to predict the other fairly well. That means the two variables are strongly correlated. So if I tell you what one value is, then I can use it well to predict the other. That is not the same thing as one of those things causing the other to happen. Right? Correlation just says that it's a good predictor. So you'll hear this. Idea talked about that correlation does not imply causation. It might be that one of the variables is causing the other to happen, but that also might be misleading. You can get a strong correlation between two variables that have absolutely nothing to do with each other. So it is up to some of the ideas we're talking about in chapter 4 and some other critical thinking things that we might talk about to determine whether there's actually a cause happening here. So in this case, on the y-axis, we have the human population going up as the number of storks in an area goes up. So as there are more storks in an area, there tend to be more people in an area. And so clearly, obviously, but that's not obviously the case. Anyone know what movie this is from?
That is from.
This is Mr. Stork bringing the baby. This is the beginning of Dumbo.
For a
And
second,
so-
I thought it was. Do you remember that? What's that one? It was like a Disney movie, I think, where it was all the mice.
The rescuers?
It was the rescuers, and there was the stork that like couldn't really fly.
Mhm.
He was like, "All right, guys, get." He was crazy. That was such a good movie. Thank you, Emily. I'm gonna watch
that
that
movie.
bro.
That reminds me of Flushed Away. Nobody remembers
Almost.
that movie, but I do.
One more thing.
Come on, just watch Flushed Away.
One more thing. What is actually happening, my smartboard's not working again.
That's what's happening.
That's what's happening.
It's the storks.
What's actually happening here is if we think about it, the causing effect is going the other way. More people in a location will mean more households, which will mean more things like chimneys and rooftops, which are fantastic nesting places for storks to be able to live and inhabit. And so what may be happening is that they may just have nothing to do with each other. Or it may be that the causation is happening in the other direction than what we may be thinking. Is this an important question?
It pertains to this.
Yes. Okay.
So could this be kind of like what you were saying with the temperature going up and it not correlating anymore? Like, because this is more of a, I don't know, suburban population. So could it get to the point where it's like a couple million people and that's a city, and so you're like, well, the stork population will drop off then?
That's possible. That's another case where we want. So the question was about extrapolation.
Yeah.
Where we might not be able to use the population to be a predictor of storks anymore when the population gets to a certain size. So that may be the case. When we talk about the beach visitors, I would say that that may be somewhere where we can talk about causation, because I think it would make sense to say, okay, there's an increase in the temperature. Well, there's a reason that we might think about for why that might cause more people to want to go to the beach. It's a nice day for the beach. We have that association and causality in our minds of that. But this idea of correlation and causation is important. It's actually what drew the tobacco companies to combat a lot of the research around smoking and lung cancer rates, because they would make the argument of, well, you've shown a correlation, but you haven't exactly shown a causing factor that this increase in smoking rate will actually be the thing that is causing lung cancer. And so they made that argument for long periods of time, and it was down to doing more studies, and we'll talk about some of those methods in chapter 4, doing some more studies to talk about what may be, showing that, yes, this is what is causing it, and here's why. So I gave a homework assignment yesterday. Let me put that up again, just to make sure we have it. And you got about 15 minutes or so.